Good afternoon, everyone. My name is YUANHAO. I'll be covering the first two sections of our presentation, setting the scene and the cost insights. Here's an overview of our day presentation. Next, we're going to part 1, challenges and model setup. Smart Wages is a startup in the small market. They face a critical business dilemma, determining the optimal production volume for their next run. The decision impacts cost, pricing, and ultimately profitability. The challenges lies in balancing production efficiency with market demand, because higher volumes require lower prices to attract buyers. To solve this, we built a mathematical model using calculus. Here are 4 core functions: total cost, which includes fixed and variable cost; price function, showing how price drop as more units are sold; total revenue; and the total profit. Next, we're going to part 2, cost insight. Now let's break down the total cost function into 3 components. The first one is fixed cost, the constant 50,000, covering expenses like R&D and setup. The second one is linear variable cost, the term 28x, representing costs like material and labor that increase directly with each unit. The third one is quadratic cost, the term 0.01 x power 2 times in cx, capturing rising mechanical cost due to factors like overtime and machine wear. To evaluate efficiency, we compare average cost and marginal cost. Average cost is total cost divided by units. It first decreases as fixed costs are spread, then rises as variable costs dominate. Marginal cost is a cost producing one more unit. We find the most cost-efficient production volume by setting the derivative of average cost to 0. Solving ACX equals 0 gives us approximately 387 units. At this point, marginal cost equals average cost, confirming the minimum average cost. However, this is the most efficient scale, but not necessarily the most profitable one. That's where marginal analysis comes in. In summary, by disposing the cost function and using calculus, we can identify the most efficient production level. But to maximize profit, we need to look beyond average cost and consider revenue dynamics, which my teammate will explain. Okay, thank you.
Teacher, I'm ZHAO. My student ID is CST92509065. Now let's talk about part 3. We will dive into the revenue drivers that shape Smart Wages' optimal production decision. Because understanding how revenue behaves is key to maximizing profitability. First, let's connect revenue to market demand. Our total revenue function is Rx equals to 6t times 0 minus 0.02 x times x squared. derived from multiplying the price function px equals to 60 minus 0.02x by production volume x. This formula tells a clear story. As we produce more units, we have to lower the price to attract buyers, so revenue initially rises but eventually peaks. Importantly, average revenue ARX equals the price function itself, meaning every unit sold contributes exactly the current market price to our revenue per unit. Now let's explore marginal revenue, or MR, the unsung hero of revenue optimization. MRX equals to 60 minus 0.04x, calculated as the derivative of total revenue. Unlike average revenue, MR is always below the price function. Why? Because selling one more unit requires lowering the price for all units sold, which reduces revenue from existing sales. This gap widens as the production scales, showing the trade-off between volume and price. Crucially, revenue maximization where MR equals to 0 isn't our end goal, profit is. But MR reveals the critical profit maximization condition, MR equals to MC. Setting 60 minus 0.04 times x equals to 28 plus 0.02 times x. We solve for x equals to about 533 units. At this volume, the extra revenue from one more unit exactly matches its extra cost. This is where revenue and cost align to deliver maximum profit. In short, our revenue drivers aren't just about selling more, they are about balancing volume, price, and marginal gains. By leveraging these insights, we turn demand dynamics into actionable decisions that drive bottom-line results.
Hello, this is CST2509054 YUANHAO speaking, and I'm going to introduce optimal decision. To determine the optimal production volume, we apply the first order condition to the profit function, this function, and then setting P prime, this its derivative function, this function, and we solved for x and found optimal production volume to be approximately 533 units. This step ensures mathematical consistency in our approach, and we then confirm this result using the second order condition. Since this one is negative, it confirms that the point we found is indeed maximum, reinforcing the reliability of our solution. And at this optimal production volume of 533 units, we calculate the following key metrics. The selling price per unit is 49.34 yuan, derived from the price function, and then the total revenue reaches this yuan, derived from this After deducting total costs, we achieve a maximum profit of 7,034 yuan, computed as this one. This production volume effectively balances cost efficiency with revenue potential, maximizing overall profitability. And then it's important to distinguish between cost efficiency and profit maximization. At 387 units, we achieved the lowest unit cost and a profit of 6,832 yuan. However, at 533 units, we maximize total profit, even though unit costs are slightly higher. This comparison illustrates a key strategic trade-off. While producing at a cost-maximizing volume saves on expenses, shifting to the profit-maximizing volume generates greater overall profit. This highlights why production decisions should be aligned with profit goals, not just cost efficiency. In summary, by applying optimization techniques and comparing different production scenarios, we recommend producing 533 units to achieve maximum profit. This approach ensures that our strategy is both mathematically sound and aligned with business objectives. Thank you.
Hello, my name is PEISEN CRT25090055. So when we talk about calculus, we often think of formulas and calculations. But in this project, we focused on a more protected question: how calculus helps us make decisions. So instead of only looking at the final answers, calculus allows us to focus on changes, especially what happens when something increases a little. This idea of focusing on change is the starting point of our analysis. In this example, we use calculus to answer a simple question. If a company produces a little more, is that a good decision or not? To answer this, we compare how cost and revenue change when production increase. By comparing these two changes, calculus helps turn a real-life decision into something we can analyze clearly. Using the given formulas, we calculated a point where the change in the revenue is equal to the change in cost. So before this point, producing more can still increase profit. After this point, producing more no longer helps. So this point represents the most suitable production level. The final results show that this output is 533 units with a maximum profit of 734 yuan and a saving price of about 49 yuan per unit. This analysis is intentionally kept simple so we can clearly see how calculus works. We focus on one main factor and assume other conditions stay the same. In real situations, decisions are usually more complex, but this simplified model is enough to show the basic idea. Overall, this project shows the calculus is not just about solving equations. It helps us compare different choices and understand which option makes more sense. By focusing on change and comparison, calculus supports clear and more logical decision making. So that's all for my part. Thank you for listening.